Hi synth lovers. Welcome back to my channel. This video is part of a series of videos in which I am designing and building my own DIY modular synth from scratch. In this video, I will explain the design of a power supply for my modular synth. The power supply is the most essential part for any electronic device. While most devices run on a single level power supply, our synth modules typically need two power levels to be able to operate, plus and minus 12 volts. Why is this different from your normal portable device with, for instance, a battery, providing only one voltage? In other words, why do we need that extra power level? The answer lies in the fact that most of the synth modules use op amps. To do their work properly, these op amps need a positive and negative power supply. Although there are a couple of ways to build a power supply, I will go for the simple and most common solution, an old school linear power supply. The design is nicely explained in a video of Moritz Klein. Moritz also extensively describes how the power supply works. If you are interested in that, go watch his video, I will leave a link in the description. This is the schematic I came up with. By the way, I am using the KiCad suite to create schematics and PCB layouts. It is an open source design suite for electronics and, although it has some quirks, it works quite well. You can download and use it for free. The link is in the description. Let's dissect this schematic. For input we will need a 12 volts AC signal. This can be provided by suitable wall ward or by a 220 volts to 12 volts transformer. The AC signal will deliver a signal like we see here. It alternates from positive to negative 12 volts. Although we do need positive and negative 12 volts, it must not alternate. I would like to have a steady, ripple-free, plus and minus 12 volts come out of my power supply. We must find a solution to split up the positive part from the negative part of the input signal. Typically, diodes are used for this. Let's now focus on the top part of our schematic, the part that provides plus 12 volts. In this orientation, diode D2 will allow only the positive part of the AC signal to pass through. The output signal looks like this. We immediately notice that this is not suitable to act as a positive power supply. We want our signal to be smoother than this, much smoother. The most common way to smoothen out the signal is by using a capacitor. The capacitor fills up almost instantly when the signal rises. When the capacitor is filled up, and the signal drops again, the voltage will be released slower into the system. How slow that happens is dependent on the load of the system. Let's look at this example. We added a 1 microfarad capacitor to the circuit. In combination with the 1K resistor that simulates the load. We see that the output signal is being affected, but it is by far not good enough. Let's try a larger capacitor, let's say 4200 microfarads. This definitely flattens the ripple, leaving us with a near perfect signal. However, if we increase the load, by lowering the resistor to about 11 ohms, we see that the signal becomes less smooth again. To counteract that, we must crank up the capacitor value to about 15,000 microfarads. Back to our schematic. We will use three 4700 microfarads electrolytic capacitors in parallel, which is equivalent to a capacitor of 14,100 microfarads. That is close enough for me. We are not there yet. We want to reduce the ripple even more. Besides that, the voltage is now about 16 volts, which is much higher than the 12 volts we need. 16 volts? We started with a 12 volt signal. How did that become 16 volts? Well, a 12 volts AC signal has a peak value that is 1.41 times bigger than the effective voltage of 12 volts. This would be about 17 volts. A voltage drop of about 1 volt is caused by the rectifying diode. Keen viewers will have discovered that these numbers are not exact, but they are close enough to get the idea. Anyway, we must reduce the voltage a bit and de-ripple the signal even more. That smells like we need some more electronics to be added to our schematic. And it turns out that we do, however the extra electronics comes in the form of a small semiconductor device, called a voltage regulator. In our case this would be of the type 7812, 78 for positive, 12 for 12 volts. This chip has an input pin, an output pin, and a pin that needs to be connected to the zero level, also referred to as ground. The result is a nice smooth 12 volt signal, capable of delivering 1 amps to our modules. But again, we are not quite there yet. Sudden increases of the load can result of a momentary drop of the voltage. The big capacitors are too slow to handle those, so we must add some smaller capacitors at the input and output pins of our voltage regulator. These are often called decoupling capacitors and they must be mounted as close as possible to the in and output pins. We must keep that in mind when designing the PCB. I will use tantalum capacitors for that. Another safety measure we can take is add an extra diode between the output and input pin of the voltage regulator. This diode will prevent that a current will flow from the output to the input through the regulator. This could happen in the rare case that the voltage at the input pin would drop below the voltage at the output pin. These negative currents can destroy the regulator. Finally, to visualize that we do have voltage on our output, I added an LED. A resistor, to limit the current through the LED, is added in series. And that was it for the positive part. The negative part is very similar, with a few differences. A 7912 regulator is used. 79 indicates that it is a negative regulator. All the diodes are reversed. Finally, all polarized capacitors must be oriented with their negative side to the minus 12 volts rail, instead of ground. And here we have the full schematic. On the input side, I will place a PCB screw terminal block. The output side will be connected to a 16-pin IDC head, which will be connected according to the Euro rack standards. A final note. I know that some Euro rack modules will need 5 volts, especially if they contain logic chips. I am building the modules myself, it is a DIY project, and I am planning to build mostly analog modules. I don't see the need to add the 5 volts to the power bus for my projects. If I do stumble upon a design that needs 5 volts, I will add it to the module's PCB and derive the 5 volts from the 12 volt supply. In the next episode, I will design the PCB layout for this power supply. All documentation that I have created for this series is available on my Patreon. This includes schematics and the Gerber files for the PCB designs and front panel designs. Thanks for watching. If you like this kind of content, consider subscribing and hit that like icon. Leave a comment if you have questions or suggestions. Or just to say hello. Have a nice day and see you in another episode.